9. And yeah, okay, so this is going to be a series of 2 lectures talking about basically high school trigonometry and just going over the subject. So I've written down sort of the contents of these talks. This is not a substitution or a replacement for lectures or lessons or doing problems. That's the real way how you learn mathematics, is doing the problems yourself, going through content until you understand it and not moving on until then. So, but that being said, if you've covered trig before or maybe want a little hint as to what it's about, I think these 2 talks should be quite nice. So in this talk I'm going to be going over sections 1 and sections 2. So we've got definitions and geometry. Yeah, I think sections 3 and sections 4, which I hope to do next week, talk more about the algebraic aspect of trigonometry, whereas these first 2 sections talk about the geometric concept. So really and truthfully, we'll be studying triangles. But I digress. Let's move away from the contents. So what is trigonometry? So I mean, if we look at the word specifically, I mean trigonometry or metry. Tri obviously means 3, gon means angle. I thought it meant shape, but so for example, polygon is a shape with multiple angles. And metry means measurements. So if you have geometry, that's geometry, so measurements of the earth. And I mean, triangles, which is going to be the study of, have a way of getting into everything. So I've sort of drawn a couple of pictures here just to illustrate that. So obviously we've got trigonometry involves triangles, but if you notice, if we describe any point on this circumference of a circle, we're going to be using triangles, right? You can see how there's a right triangle embedded into the circle, so the trig functions apply. Similarly with projectile motions or kinematics, dynamics of particles, so applied maths, whenever you use angles, trigonometric functions will be involved. So often in terms of looking at kind of the horizontal movements, you're using sines, and did I say horizontal? Vertical movements, you're using sines, and horizontal movements, you're using cosines. So the physics aspects are strong. And also, you might not believe it, but right now we're using some applications of trigonometry, something which is closer to my own research, has to do with kind of Fourier Transforms, which is, in simplicity, very useful with image processing. So you have an image, and each kind of point on, you can think of an XY plane or a coordinate system, has some information associated to it as to how to render the picture. But there's lots of different ways you can describe the picture to the computer for it to then display it. And this is kind of 2 different ways. The one on the right has to do with frequencies, which is all about the trigonometric functions. And you notice it's a little blob. And one reason why this is super useful is for video compression or audio compression, because there will be lots of little contributions, if I use a little pen, lots of little contributions here and like over here and over here, which make such a minimal effect on the picture that you can truncate them. You can just get rid of them altogether, set them to 0, and then they don't take up memory on your computer, and you still have a pretty good image when you map back. So these are some applications of trigonometry and reasons why you might be interested in studying it. But for the contents of this talk, I'm interested in, let's use that, starting from the beginning. So let's look at some definitions just before you tackle trig. So things which you should be familiar with are facts like angles along a straight line add to 180 degrees, right angles are 90 degrees, interior angles of a triangle sum to 180, and there's like a nice generalization with polygons. I'll illustrate it here just in this quick example. Suppose you want to find the sum of these interior angles, right, of a regular pentagon. Well, a trick we can use is sort of, if you take this point here and just split the region up into triangles, well, we know up here that the interior angles of a triangle sum to 180 degrees. That means this angle plus this little angle here, plus this little angle here, that sums to 180 degrees. This angle here, plus this angle here, plus this angle here, also sums to 180 degrees. And finally, this angle here, and this angle here. So we know that the sum of the black angles, the sum of the green angles, and the sum of the red angles independently all sum to 180 degrees. And when you add them all together, notice how you actually cover everything and nothing else of the interior angles of the pentagon. So the sum of all these angles is the interior angles of a regular pentagon, and we know that this is just 180 plus 180 plus 180, which I believe is 540 degrees. So just a brief little recap of some basic geometry before you get into trigonometry. And similarly, we also have corresponding and alternate angles. You can kind of see the red ones are corresponding, the blue ones are alternate. They are equal. And finally, we have this sort of terminology when two triangles are similar, it means they are scalar multiples of one another, right? We just take one triangle and just enlarge it by a factor of k. So here I've used this kind of congruence notation, but if that seems intimidating, it's fine. But yeah, so this, I will be repeatedly coming back to this, but I don't want to spend too long on the prerequisites, so let's start. So, I mean, straight from the definitions, what the trig functions do, what sine, cosine, and tangent do, is if you have a right triangle, you label an angle, which I've called x, and then you can label the triangle itself, right? The side opposite to the angle is called the opposite. The side adjacent to the angle is called the adjacent, and the side which is the longest is called the hypotenuse. And this is for a right triangle, meaning that there's a right angle here. And what the trigonometric functions do is they give you, if you input an angle of this right triangle, it will output the ratio of two sides of this right triangle. So sine of the angle is going to be this opposite side divided by the hypotenuse. Cos is going to be the adjacent divided by the hypotenuse, and the tangent is going to be the opposite divided by the adjacent. A nice kind of way to remember this is SOHCAHTOA. That's how I remembered it in school, but I will just be recording it from memory here, so you don't need to remember it from this lecture, but you will definitely need to learn it if you do a course in trigonometry, or if you already have done, I imagine you also remember it too. Why are these useful? Well, it allows us, given certain right triangles, to find other sides. So, for example, let's try and find the side B. Well, this is, if we label the triangle, we have the hypotenuse is our side A, the opposite is our side of length 1, and our adjacent is our side B. If we want to find the length A, then we want to incorporate information that we know, the angle, the opposite, and the hypotenuse. Well, the trig function that incorporates the angle, the opposite, and the hypotenuse is the sine function. So if we just naively write down sine equals opposite over hypotenuse, well, now we can start plugging in values, right? Sine of 30 equals the opposite, which is 1, divided by the hypotenuse, which we don't know yet. It's just A. In fact, let me type A specifically. Ooh. Now we can solve for A, so we multiply both sides by A, divide through by sine of 30, so we get 1 over sine of 30. And then we can plug this into our calculator. I've got my little calculator here. 1 divided by sine of 30. And this is just a length of 2. So yeah, I'm not going to go through length B due to time, but you can see the method which I've applied, right? I've looked at the triangle which we have, the information which we want. So we have the angle, we have the length of the side, we have the length which we're trying to find, and this corresponds to the angles opposite. I don't know why I've called that odd. The angle, the opposite, the hypotenuse. the sine function incorporates all of this, and then you just write down the sine function, plug in the information you know, solve for the unknown, and then plug into the calculator. So something which I found quite unsettling when I first did trigonometry is I thought this was almost witchcraft. How can you just, for any triangle, any size you want, which is a right triangle, that you can somehow plug in the angle and you just so happened it makes sense to find the ratio of two sides? Like, why? How can this be true? Surely if you have two different triangles which have the same angle, maybe the trig functions equal something different. And the point of this little illustration here is to say, well, actually no. If you have two triangles which have the same angle, so we have a right angle, we have the same angle x, notice that also this angle is completely determined, right? Because the interior angles of a triangle sum to 180 degrees. So this is just going to be 180 minus 90 minus x. So this is just going to be 90 minus x, and that's the length of your angle. And similarly, this is going to be the same. This is going to be 90 minus x. And so because the triangles have the same angle, interior angles, they're going to be similar triangles, right? One is going to be a scalar multiple of the other, and that scalar multiple I've written down to be k. So using the fact that we have a right angle, or two right angles, it's like two right triangles with two of the same angles, x, we know that they are going to be scalar multiples of one another. And so when we naively apply, let's say, the sine function, which gives you opposite over hypotenuse, here our opposite is going to be k times the opposite and k times the hypotenuse. But when I divide through, these k's cancel. And so the sine of the angle of this triangle, which is here, is exactly the same as the sine of the angle of this triangle. So I just wanted, and you can give the same arguments with cosine and tangent. But the point here is that, yes, the trig functions make sense. It's well defined to apply this to any right triangle willy-nilly. A lot of students who first tackle trigonometry find the trig functions a bit awkward, because how do you actually calculate them? I mean, obviously we have a calculator which we can plug things into, and it makes sense to now, given an angle, output the ratio of two sides. But how do you actually compute it? And this isn't an easy question. There are things I can say about approximations using different techniques. In calculus, you look at something called Taylor series, and all of this fun stuff. But a nice way is just to draw any triangle. Say you want to calculate sine of, I don't know, 20. Just draw any right triangle which has an angle of 20. Finish the triangle, so make this just make the sides long enough that you can create the right triangle. Measure the sides with a ruler. Say I want to calculate sine. I'll measure the opposite and the adjacent. Sorry, the opposite and the hypotenuse. So this could be, I don't know, A and B. So A and B are sides that I've measured, and therefore sine of our angle that we want to calculate, we can approximate it using what we've measured of A and B. Right? It's just going to be A divided by B. So that's how you actually calculate the trig functions. You just draw a triangle with the angle you want to calculate, and then the trig function evaluated at that angle is going to be the ratio of these two sides that you've measured. Often before we had calculators, you'd have these sort of books that you open, and they'd have lots and lots and lots of different angles and approximations for each of the corresponding trig functions. So let me just look and see if we have any questions. What is k? Up here again, it's k is the scale factor of the right triangle. So since these have the same angles, they are similar, which means one triangle is a multiple of another. For example, this triangle could be twice as big, in which case all the lengths would be twice as big, so k would be 2. You'd be multiplying each length by 2, and that's what it means to be a scalar multiple. So those are what the trig functions are. Right? We can use them to find sides of right triangles, and conversely, we have the inverse trig functions, which instead of given an angle and maybe some side, you can find another side. The inverse trig functions say, given two sides of a triangle, we can find the angle. And you basically just do the exact opposite. Instead of plugging in the angle and getting this ratio, you plug in the ratio and get this angle. So let's just naively do an example, assuming that all of this is well defined. Let's find the angle x. So we have, again, we'll label our triangle, we have an hypotenuse, we have an opposite, this is opposite to x, and then we have an adjacent. Obviously, if we're looking at y, then the opposite would be this side, and the adjacent would be the vertical side. So if we're wanting to find x, and we've labeled our triangle, we're going to need to use, well, we have the hypotenuse and the adjacent, so we want to use the cosine, because we have the adjacent, which is 2, we have the hypotenuse, which is 4, and finally then we'll have the angle, which equals x, and then we can just plug this into our calculator. These are triangles I am supposed to know off by heart, but I don't want to risk it, so plugging this into the calculator, you then get 60 degrees. So again, what have we done? Well, we've used the inverse trig functions to find angles given two lengths of a right triangle. We've labeled our triangle hypotenuse, adjacent, opposite. We have two pieces of information. We know the hypotenuse and we know the adjacent, so cosine automatically shouts out, and then you just apply the trig function. And as I mentioned just now that I should know these triangles off by heart, these are two triangles you should really have in the back of your mind when doing a course in trigonometry. So here we have what's called the Isosceles right triangle, where we have two equal sides, which means these two lengths are equal, and finally we have a right triangle. So it forces the sides to be, the angles to be 45, 45, 90. And you can show by Pythagoras Theorem that this is going to be the square root of 2. And similarly, because of our congruent triangles here, that we might have other triangles with the same angles, 45, 45, 90, but our sides may be scaled up. So perhaps we have 2, 2, and then 2 times the square root of 2. I mean, you can simplify that in a calculator if you want, but I like to keep it in surd form. And so this makes sense. So they have the same interior angles, but they might be scalar multiples. And this is, again, because they're similar triangles. Here we have a scale factor of 2. So yeah, we have a similar right triangle here, where we have 30, 60, and 90, called the 30, 60, 90 triangle, funnily enough. And yeah, we can figure out the sides. I mean, if you draw this triangle with one side length of 1, then you can measure everything else with a ruler. So let's try and use these triangles to our advantage. And I'm not going to do all of these questions just for the sake of time. Oh, have I got a message? Is that a question? No. Okay, cool. Yeah, so let's use these triangles to try and find exact value of some of these trig functions without having to use the calculator. So, I don't know, let's use sine of 30. How are we going to do sine of 30? Well, because our angle is 30, we're going to be using this 30, 60, 90 triangle. And because it's a sine, sine is going to be opposite over hypotenuse. That's the definition. And for the 30, 60, 90 triangle, our opposite side is going to be 1. So this is going to be 1. And our hypotenuse is going to be 2. So sine of 30, the exact value, is a half. We've just stated what the definition of the sine function is. We've observed the triangle, which we know all about. We know its angles and we know its sides. And so we plug in our values and get 1/2. I'll do one more example. Let's do tan of 45. Again, tan is opposite over adjacent. And so if we take, I don't know, this angle 45, the opposite is going to be 1, the adjacent is going to be 1, so this is just simply going to be 1 over 1, which is 1. So we can find exact values by just comparing it to these triangles that we know. And similarly, if we look at this next example, let's pick, I don't know, cosine inverse of the square root of 3 over 2. If we look at this side, we only have square root of 2, 1, 1, but here we have a square root of 3, so it makes sense to use the 30, 60, 90 triangle. And we can see that it looks like we have the square root of 3 here divided by 2. So what angle does this correlate to the cosine functions? Well, here, if we pick the angle 30, then where's the eraser? If we pick the angle 30, cosine of 30 is going to equal to adjacent divided by the hypotenuse. The adjacent here is the square root of 3, the hypotenuse is the square root of 2, and if you compare it to what we have here, well, cosine of 30 equals this ratio, which means that the inverse, if we go the opposite direction, the inverse cosine of this ratio is going to equal 30. And that's how we get it here. I encourage you to have a play around with these problems. It really is just identifying in the fraction which sides correspond to the hypotenuse or the opposite or the adjacent, and then how do you bring it together to get the sine or the cosine or the tangent functions. So now finally I want to have a look at this problem here. This is quite a, a bare bones example of a trigonometric problem where you have a river and you are on one side and one side only. You cannot cross, but you may be interested in knowing what is the width of the river. So what you could do is you could kind of mark where you think the rock is, or the end of the river is directly opposite to you, so this is going to be a right triangle, and then you move some distance, in this case we've moved 30 meters to the left, and then we've sort of taken a bearing. We've looked at that same point here, and we've seen what the angle is. And so what we've done with our observations is we formed a right triangle, but what's cool is we formed a right triangle where we have enough information to find the rest of the sides. So if we use the trigonometric functions on this right triangle, let's say 30, this is 40 degrees, and we want to find what this side is, well, this is the opposite, this is the adjacent, and this is the angle, so we know that the tangent of the angle is going to equal opposite divided by the adjacent. Well, the opposite side is our unknown, this is what we're wanting to measure, but the adjacent side is going to be 30 meters. So solving for the unknown, the opposite side, which is the length we want, the opposite is going to equal tan of 30. Did I say 30? It should be 40, apologies. 40 degrees, there we go. There we go, opposite equals tan of 40 multiplied by our length here. So this is, again, we've applied the definition for the tangent function, and then we plugged in the values which we know, and then we solve for, of course, this opposite side, which is the height of the triangle, or in this case, the width of the river. And then we simply plug in our values. So if I plug in tan of 40, yeah, I have plugged in degrees here. So this is approximately 0.839. And then when we multiply it 3 by 30, we should get something like 25.17 meters. And this is to 2 decimal places. And that gives you the length of the river. So using trigonometry, we have found how wide the river is by simply just being on this side of the river, which you got to admit is pretty neat in terms of like, you'd think normally you'd have to somehow cross the river or have a piece of string or measure it with a ruler in order to figure out its width, but you can do it without crossing the river at all. And similar ideas if you maybe have like the sun and you're over here and then over here and you have this very, very small angle, you might be able to approximate how far the sun is away from the earth, or at least where you're standing. So in summary of this section, which is section 1, I am looking to see if we have any questions. What we've done is we've introduced the trig functions, so their definitions, which are all about right triangles. It's all about, given an angle and perhaps another side, we can find everything else. Another way of saying that is, given 3 pieces of information, the right angle is one piece, the angle is another piece, and the side length is another piece, then we can use trig to just classify what the triangle is, use all the other lengths of the sides, find all the angles using the inverse function, so we now completely understand right triangles. What did you plug in to find the opposite? In this situation, well, we formed a right triangle, right? So we don't, a priori, we don't know what the side is, we call it h, let's say. And so we have a right triangle. We label it the hypotenuse, the adjacent, the opposite. We want to find the opposite. We know what the adjacent is, and we know what the angle is. And we just happen to have a trigonometric function that has a relationship between the opposite, the adjacent, and the angle, right? This is the definition of the tangent function. So without even plugging anything in, except I plugged in 30 again for some weird reason, without plugging anything in, we have this relationship, and then when we do plug things in, right, we want to find the opposite because this is the unknown, but we know what the adjacent is, which is 30 meters, and so we can solve for the opposite by by multiplying both sides by 30. So we then get 30 times tan of 40, and plugging this into the calculator gives us 25.17. So that's how we did it. So again, we had a triangle, we've observed that we know what the adjacent is, we want to know what the opposite is, and we know what the angle is, and the trig function that brings all of that together is the tangent function. So we just state the tangent function, plug in the information that we know, and then solve for what's unknown, in which case is the opposite, and this happens to be the length of the river. So that's the point of the basic trig functions, right? To study right triangles where we may or may not know the angle, but we know at least 3 pieces of information about this triangle. The next section is trying to generalize this. Okay, so we now know how to study right triangles. We use the definitions of the trig functions. But what if our triangles aren't right triangles? What if we don't have that right angle of 90 degrees? So I'll start with Pythagoras' theorem, somewhere familiar to all of you. This just simply states that given any right triangle, the square of the hypotenuse is equal to the sum of the other squares. You might have seen this more geometrically, is if you kind of have a square here, and then a square here, and then a square here. And right, these corresponds to just like, if this length here is, I don't know, 3, then the area of this triangle is 3 times 3, which is 9, so 3 squared. So what Pythagoras' theorem states is that the area of this square is equal to the sum of these 2 areas. So a squared plus b squared equals c squared. Now I don't know how many of you would have seen a justification for this. I can't remember at school seeing our teacher justify it. This isn't a proof per se, but it's a justification. And the way I sort of justify it is I take our arbitrary right triangle and I just construct this monstrosity. I take the right triangle, I rotate it, and then I have a big square with a side length a plus b, and I have a square in the middle with a side length of c. And so let's find the area of the big square. For the area of the big square, we can use two methods. The first methods, we can just use base times height. So this is a plus b all squared. We can distribute this, so this is going to be a squared plus 2ab plus b squared. And that gives us one expression of the area in terms of its side lengths. Another method for finding the area is finding the area of each of these triangles individually. So this is going to be 1/2 base times height, so base is a, height is b, and then we just multiply them together and take a half. We have 4 triangles, so we add them together or multiply them by 4. And then finally we add the area of this interior square, which has an area of c squared. So this is just another method of finding the area of the big squared. We take the area of the 4 triangles plus the area of the interior square, and this gives us this expression if we simplify. But it doesn't matter which method we use, because we're just finding the same quantity. We're finding the area of this big square. So we can set them equal to one another, right? This expression equals this expression. But by simplifying the 2ab, because we can just subtract it from both sides, what we end up with is that a squared plus b squared equals c squared. And this is exactly the relationship we're trying to show. And because we've used arbitrary triangles, we didn't pick a specific one, we just picked any right triangle and did this geometry construction. This holds for any right triangle. And that is a justification of Pythagoras' theorem. There are many out there, and again, it's not a proof, because I would want a little bit more argument as to why we can always make this construction, but it's a nice geometric intuition as to where Pythagoras' theorem comes from. And the reason why I've spent about 3 minutes on Pythagoras' theorem is because the cosine rule, or the law of cosines that you may have seen before, is in essence a generalization of the Pythagorean theorem, but for non-right triangles. So notice our side C is equal to a squared plus b squared again, but we have this error term, we have something that corrects it, because this by itself isn't always true. It is true for right triangles when our angle x is a right angle, but it isn't true when we just have any arbitrary triangle. So I've stated it for now, and we're going to quickly do an example. So we want to find this side length c. Well, we'll use our formula up here, we'll use the cosine rule. So a squared, which, I don't know, we'll pick as 8, so a squared is 8 squared, plus b squared, which is 11, and then we minus 2, 8, 11, times the cosine of this angle 37. Okay? So again, we can plug this into a calculator. So I've got my calculator here. So 8 squared plus 11 squared, take away 2, times 8, times 11, times the cosine of our angle 37. And this seems to be about 44.44. And then we square it both sides to get c by itself. So if we square root our answer, we get a side length of a roughly 6.66. And that's the 2 decimal places. And that's our side length here. So we have applied kind of our generalization, if you will, of the Pythagorean theorem to find this side length of this arbitrary triangle. Notice again that we have 3 pieces of information about the triangle, and with those 3 pieces, we're now finding any other side. So I'll quickly look at questions. Okay, it doesn't look like this. Cool. So now let's do a little bit more justification, because I've just stated what the cosine rule is. Why is it true? Why does the cosine rule hold? Well, we can draw sort of our triangle, our arbitrary triangle, and just lay it horizontally on this side. And then we can draw this new line completely down, which bisects this angle nicely, so we have sort of two right triangles. And the method we're going to use to justify the cosine rule is just to play around. That's how most maths is discovered. You just play around and these identities pop out. And the way I'm going to play around is I'm going to use the Pythagorean theorem on this left triangle. So that gives us h squared. So you can think of this as h squared plus t squared equals a squared, or if you subtract t from both sides, we get h squared equals a squared minus t squared. And similarly, we can use the right triangle to find an expression for h squared. So again, I've used Pythagoras Theorem, but I've simplified a little bit. But again, either approach we take to find this sort of altitude of the triangle, h, should give us the same value, so we can set them equal to one another, right? H squared in this way is equal to h squared. So by sort of transitivity, we can just set these two things equal to one another. We can, of course, kind of take away the t's. We can add b to both sides, subtract 2bt from both sides, and we get this expression. And so what's left to do is figure out what t is, because we're trying to justify this cosine rule, which has the sides of the triangles and the angle, but we've written down this extra piece of information t, which we don't know yet. But we can solve for t, right? We can look at this left triangle, which is a right triangle, and we can use our rules of trigonometry, right? Cosine is equal to the adjacent divided by the hypotenuse. T is our adjacent, a is our hypotenuse. And so we can solve for t. T is equal to a times cosine of x, which matches up here. And so when we plug this into our expression here, we get this expression. We get the cosine rule. We get this generalization of the Pythagorean theorem. And that is our justification. That's where the cosine rule comes from. And you'll see this triangle pop up again. So we've got the trig functions that allow us to understand right triangles. We have this cosine rule that allows us to study arbitrary triangles. But given this sort of three pieces of information, can we find everything else about the triangle? We're not quite there yet. There are still cases where we can't apply the cosine rule. So for example, perhaps we may have two angles and one side, right? The cosine rule doesn't say anything about two angles. We need the sides in order to calculate unknowns. So this is where the sine rule comes in, and it sort of finishes our classification. We can then understand any triangle if we know two angles and one side. Notice that if we know two angles, then we know the other angle, right? Because the sum of the angles is equal to 180. So 180 equals x plus y plus z. But suppose we don't know z. Well, we know what x and y is, right? We can just subtract those from both sides. We know what this right-hand side equals, so we know what z is. Okay? So the point being is now we want to understand this sine rule. We'll do a quick example. So here we have a right triangle, not right triangle, we have just an arbitrary triangle, and we want to find x. If we look at the sine rule, notice how this opposite side, oh wait, no, this is going to be opposite angle. So we need this angle here, which I'm going to call, I don't know why I called this x, I'm going to call this angle A. Well, we know what A is, because the interior angles of a triangle add to 180. So A plus 95 plus 53 equals 180, so we can just sort of subtract it. 80 minus 95 minus 53, which I think on the top of my head is going to be 32. Yeah, that seems about right. So our angle A is 32. Why have I found this angle? Well, I found this angle because now we can apply the trig functions. Sorry, the sine rule. So here we have kind of the sine of 32, and then we divide it by the opposite side, right? So this is going to be x. In the same way, when we look at here, if we have this angle here, let's say y, then we divide it by b. So we have our angle y, and then we divide it by the opposite side b. And similarly, we have our angle 95, so sine of 95, and we divide through by the opposite bit, which is 21. And so we can solve for x, right? We can just, well, what's a good way? We can multiply both sides by x, and we can divide through by this. And if you're up in your algebra, you'll notice that this will be 21 sine of 32 divided by sine of 95. And we can plug this into our calculator. If I plug this in, 21 times sine of 32 divided by sine of 95, I think it is. And this should give us a side length of 11, which sort of makes sense. So this is our side length. Why does it make sense? Well, notice how if I draw, I don't know, well, this triangle here, let's draw a more extreme version. Let's do x and y. Notice how here y is the largest angle, right? It's the biggest. But the side length corresponding to y is also the largest side length. And similarly, x is kind of, it's a small angle, and the side length here is kind of small. So if you look at our example, notice how 95 was by far our largest side, our largest angle, and so this corresponds to the largest side, which is 21. So when we have a very, very small angle, 32, then our length, which it corresponds to, is relatively small as well. It's 10 less than 21, pretty much. So we can look at our answers and justify, okay, yeah, this sort of makes sense. I'm happy with our answer. And again, I've got a justification as to why the sine rule is true. We can draw our arbitrary triangle with one length on the bottom. We can kind of draw our altitude line, which dissects this bottom at a right angle. And again, yeah, we can play around, we can mess around and solve for this height, h, or we can use this left triangle. Notice how h is the opposite. We have the hypotenuse, which is c, and we have an angle, so we can use the sine function to solve for this length. And similarly, if we use the right triangle, we can apply the exact same argument. This is the opposite to this angle z, we have the hypotenuse a, and so we can then solve using our sine function. So we've calculated h in two ways, but it shouldn't matter what way we calculate it. So these two calculations should be equal, and by dividing through by our side lengths, we get this identity. We get that the sine divided by sine of this angle divided by its opposite side is going to be equal to the sine of this angle divided by its opposite side. And we could have oriented the triangle in any way we wanted, so the same argument holds if we want to find sine of y over b. So we have then the sine rule. And this completes our classification. What do I mean by that? Well, given any triangle, doesn't necessarily have to be a right triangle. If we know three pieces of information, so suppose we might know an angle, suppose we might know a side, and suppose we might know another angle, then we can use the sine rule or the cosine rule, or if they're right triangles, we can use the trig functions to find every other piece of information. We can find this angle, we can find this corresponding side, we can find this other corresponding side. By stating those three pieces of information, we have uniquely defined what the circle is and therefore can start measuring everything else. Except for two cases. So our first case I alluded to earlier, and that is if you have two triangles with which have equal angles, they might have different length sides. However, they will be congruent. So if we have our side length, I don't know, 1, 2, 3, not drawn accurately. If we have another triangle which has the same angles, we know that this is going to be some scale factor of this first one. So if we multiply each side length by some scale factor k, so if you are given the three angles, you won't be able to figure out what that triangle is, but you will be able to figure out what it is up to a scale factor, up to congruence. The other ambiguous case, which is less known, is when you're given two sides and one angle. So notice we have drawn two triangles which have the same angle, the same side length y, but also has the same side length z. In this case, this length here is not the same length here. So these are two fundamentally different triangles. So we need to be careful that in problems where we are given two side lengths and one angle, which triangle are we talking about? Are we talking about this triangle where all the interior angles are acute? Or are we talking about this triangle where we have two angles which are acute and one which is obtuse? But that completes our classification. That is sort of, now we know how to find all side lengths and angles of not just right triangles, but using the cosine law and the sine law, we can now classify all triangles except for these ambiguous cases. So now we know how to study triangles, we can apply it to some geometry problems. So let's just look at the time to see how quickly I need to go through. We started 5 minutes late, so we have a little bit longer than 5 minutes. Are there any questions? I am rushing through this at the present moment. Is there a tangent rule? Just wondering. I don't know. I imagine there are lots of rules which relate tangent functions. We will see in our section 4, which I'm not going to give that lecture today, that there are rules that relate side lengths and angles and the tangent functions. So this is sort of a tangent function identity. So there are rules including the tangent functions. But in terms of these identities, which we've just shown, no, there isn't one that's standardly taught. I don't think there is one. There might be, but I'm not sure. But we don't need it in order to classify all the triangles, so you're typically not taught it if there is one. But I know, I like that question. I'll have a look. Thank you for that. So now we know how to play with triangles. We can finish our lecture by looking at some geometry problems. But before I do so, I want to just allude to another way to measure rotations or angles. And that's the measurement of radians. So if you look in our sort of left diagram, a full rotation is 360 degrees. Right? We picked 360 because it has lots of factors. So if we want to describe a right angle, we just simply divide this into 4. And 360 is quite a composite number. It has lots of factors, so you can divide it by 4. It gives you 90. If you want to divide it into 3, we can find 1/3 of a rotation is just 120 degrees. Excuse me. And why 360? Because there are other composite numbers out there. 360, I believe, was picked because it also sort of relates to how many days there are in a year. It respects the the geometry of our planet, if you will. But another measurement is, instead of taking a full rotation to be 360 degrees, another unit could be radians, where our full rotation is 2 pi radians. Excuse me. So, for example, instead of our right angle being 90, which is just this thing divided by 4, we could divide this thing by 4, and that gives you pi over 2 radians. That's a right angle. Or if we wanted to do 1/3 of a triangle, we could divide this into 3. There is a way to convert between the two. I don't like thinking about a formula. I like thinking of this kind of, well, logically speaking. I mean, if you have an angle, let's say 60 degrees, what's a nice way of justifying it? Yeah, if you have an angle of 60 degrees, we can sort of, if we divide everything by 360, so if we divide everything by 360, then every 1 degrees gives you 2 pi over 360 radians. So if we divide, so if each degree is 2 pi over 360 radians, then 60 of them is going to be 60 times 2 pi divided by 360 radians. And this is 6, right? So 60 divided by 360 is 1 over 6. So this simplifies to 2 over 6, or pi over 3. Okay? So that's kind of how we convert between. You can sort of think of how many radians are there to 1 degree, or conversely, how many degrees are there to 1 radian, and then apply the sort of transformations back and forth. So an example could be, let's label this 30, 60, 90 triangle, but do it in radians. So for simplicity, let's suppose this is the square root of 2 side, this is the 3 side, this is the 1 side. So this corresponds to our 30, 60, 90 triangle, one of our nice ones. So we know that our angle should be 30 and 60. The longest side should correspond to the largest angle, so I think that this would be 60, this would be 30. But we want to convert it to radians. So what's 30 degree in radians? Well, there's 2 ways we can go about doing it. The 30 degree in radians, well, we can go from degrees to radians, so we can just do what we did before, which is just multiply through by each degree is 2 pi divided by 360 radians. So if we have 30 of them, well, this is just going to be pi on 6. So this angle here is going to be pi on 6. What about this one here? Well, instead of thinking about it in terms of this sort of transformation, notice how if you think of a whole thing being 360 degrees, well, 60 is going to be roughly about here. That's going to be 60. And that's 1/6 of the entire rotation. That's 1/6. So if we want to find the same angle in radians, well, we know that the whole thing is 2 pi units, and that this angle here is 1/6 of 2 pi. It's the same ratio, so this is just going to be pi over 3. And if you notice, we actually did convert this 60 degrees into radians beforehand. So our method checks out. We have the same radian measurement, so we can this is pi over 3. And that gives us our 30, 60, 90 triangle in terms of radians. Why might we be interested in radians? Like, this seems like an arbitrary measurement, right? Everything was fine with degrees. Why are we suddenly bringing in 2 pi units? Well, it's sort of more natural. The circumference of a circle is 2 pi r, right? Or, yeah, it's 2 pi r. So when you're looking at these sort of angles with the radius here, it sort of makes sense to somehow use this length, the circumference or the specific length here, to understand the angle, instead of just assigning some ratio 360 to relate the units to the natural geometry of the circle. And the way I've kind of justified this is to derive the arc length formula. I've derived it in 2 ways, one where our angle is in radians, which we often denote as rads, or the other way where I've put it as degrees. And so this length, right, the length here is going to be, well, it's going to be the ratio of this length and the whole circumference. So there's going to be some sort of ratio. How long is this length compared to the whole circumference? And therefore, you just take the whole circumference and multiply it by that ratio, and that gives you this arc length. But another way you can think about that is, well, the ratio of this arc length is the same as the ratio of the angle. So here, our ratio here, we have kind of our angle x, and we'll compare this against a whole rotation, and this will give us how big this angle is compared to the whole rotation, which is this quantity here. But if we multiply this ratio by the entire circumference, this will give us the ratio, or no, this will give us what proportion this line is. It will actually give us the length of this arc. So if we multiply the proportions together, we'll then get this arc length. That was a terrible explanation, but I hope that the visuals make sense. That if we look at this circle, for example, and we want to find this length, well, we could find the length of this line compared to the length of the whole line. We'll find that ratio, and then to simply find the arc length, we just multiply this ratio, or let's not use arc, we'll multiply this ratio by the whole 2 pi r, and this should give us the arc length L. So what is this ratio? Well, it's the same ratio to the angle compared to a full rotation. So we take this angle measured in radians now, divide it by the whole rotation, and then multiply it by the circumference. So this is here, this is our ratio, and that gives us the arc length. But notice, because we measured in radians, it doesn't simplify any further. We get pi divided by 180 times our angle in degrees times our radius. So you can sort of see why radians is more natural. Notice how the arc length formula just is so much nicer. And this kind of gives us what radians are, in that if we have a circle segment, 1 radian is simply going to be, well, if you look at it here, the arc length is going to be the radius times the angle. Well, here the arc length is going to be the radius 1 times the angle r, which is r. So if you were, I don't know, some person positioned here, and you were watching someone else walk around you, the length of which they walked, in terms of our unit, which is the radius, is 1 radian. So for example, I don't know, maybe you have, again, the same segment, but our radius is 1. Well, what is 1 radian? Well, 1 radian corresponds to walking 1 unit along the circumference. And that's what the measurement is. You almost get this sort of polar triangle, if you will. And that's sort of why radians are more natural than degrees. It can get quite awkward to start off with, but your formulas turn out quite nice. And you express angles using the intrinsic geometry of the circle. So how much time have we got? Okay, I've almost gone over the hour, so I'll try and speed up a little bit. There's not much left now anyway. So recall from basic geometry that the area of the circle is pi r squared. We know that the radius is 2 pi r, but the area of the circle is pi r squared. We use the same circle constant pi. Why is this true? Well, let's take the circle and split it into pizza slices, and then reorganize those pizza slices into this sort of slither. These lengths here, let's not use, these lengths here, so this sort of arcs, correspond to these arcs on the circle. So notice how the arcs along one side correspond to half of the circumference. So the whole circumference is 2 pi r, so half of this is just going to be pi r. And similarly, these lengths here are the lengths of the slices. These are the radius of the circle. Now this sort of looks like a rectangle if you squint. But if you use more slices and do the same trick, again, right, these arc lengths on one side correspond to the arc lengths along the circle. So again, this length is pi r. Oh, not 2 pi r, sorry, pi r. And this length here is the radius. And we can take more and more and more slices, and look how our shape is getting closer and closer to a rectangle. Until supposedly you take infinitely many slices, as you notice by this blob, and in which case you do have a rectangle. It's arbitrary close to a rectangle. The error is insignificant. It's negatable, sorry. And again, this side length here corresponds to sort of half the circumference, which is pi r. This length here corresponds to the radius of the circle. So in order to derive this kind of why is the area of the circle pi r squared, well, the area of the circle is the same as the area of this rectangle. But the area of this rectangle was base times height, which is r times pi r, which is pi r squared. And that gives you the area of the circle. That's where it comes from. And this sort of argument is a very calculus-like argument. So what other parts, what other areas of circles are we interested in? Well, we're going to be looking at sectors and segments. So how do we find the area of a sector? Well, again, we're going to use this proportion argument. The area of this sector is going to be some proportion of the whole area, right? This is going to be some proportion. So this area is going to be some proportion. That proportion is going to be the same as the proportion of this angle compared to the whole rotation. So suppose that this angle is x, the whole rotation is going to be 2 pi. So the ratio of this area compared to the whole area is going to be the same as the ratio of this angle divided by the whole rotation. So this ratio here is going to be the same as sort of the area of the segment divided by 2 pi r. Making sure that I have everything. Oh, sorry, not 2 pi r. Sorry, that's the circumference. The area of the circle is pi r squared. We literally just derived that. And then we solve for what we don't know, right? We solve for area. Because those two ratios are equal, we multiply both sides. Notice that the pi's cancel, and we're left with pi r squared over 2. And that's where this area comes from. So this is how you find the area of a sector, given the angle here and given the radius. Before we want to find the area of the segment, we can use trigonometry to find the area of a triangle. So here, if we have any triangle whatsoever, it doesn't need to be a right triangle, we know that the area is 1/2 base times height. But suppose we may not know what this altitude length is. We only know the sides of these triangles. Well, we can describe h using our trigonometry, right? We have our angle, we have our hypotenuse, and we have our opposite. So h is going to be a times sine of x. This is how we get the trig function. So h was our unknown, but we know what a is, we know what x is, so we know what h is. And then we can plug it into our formula. So area equals 1/2 b times a sine of x, or rather area equals 1/2 ab sine of x. So that's how you find the area of the triangle. We will go through an example in a moment. I'm just sort of rushing through at this point. And that gives us enough to find the area of this sector. So the area, sorry, segment. So if we want to find the area of the segment, we'll notice that the area of the segment, if we take this is the sector. And perhaps we're interested in, well, we'll then draw the triangle. So we have the area of the sector. we have the area of the triangle, and if we subtract the two, if we take the whole sector and subtract this area of the triangle, then this gives us the area of the segment, right? And so that's what we do. Area of the segment is the area of the sector, subtract the area of the triangle. Well, we found what the area of the sector was. It's half x times r squared. It's important that x is in radians. And then we subtract the area of the triangle, which is 1/2 r squared sine of x. And then we just sort of collect the like terms, the common factors, and we get the area of a segment. So now we have a nice example. Almost to the end, but I'll go through this example. So how do we find the area of the shaded region? This is 3 segments. Segments. There's multiple ways of doing it. You can try and find the information you need in order to use the segment formula, which is here. You could, what I'm going to do is find the area of this triangle. How would you do that? Well, if you notice that this is pi on 3, this is pi on 3, this other angle also must be pi on 3, because the interior angles of a triangle add to 180, or in this case, the interior angles add to pi, because 180 degrees is pi units. So if we know what those two angles are, and we know that all of them add to 180, then we need to add another pi on 3. And because the angles are the same, we know that this is an equilateral triangle. Which means if we sort of draw another line here, and another line here, that because this is an equilateral triangle, all of these angles are the same. Right? This is a full rotation, 2 pi, so divide 2 pi by 3, because each angle is the same. That gives you the angle. And so now we find the length of this triangle. So the length, the area, the radius is 1, so this length is here is 1, this length is 1. Here our angle is going to be 2 pi on 3. So the area of this triangle is going to be our triangle formula, which is 1/2 AB sine C, well 1/2 AB, which is 1, 1, and then we take sine of 2 pi over 3. And when you're calculating sine of radians, it's always good to just check that your calculator is in radians. Why? Well, because obviously if you have sine of 1 degree, this is not going to be the same as sine of 1 radian. So often we'll put a little like dot there to indicate that this is degrees. They're not the same. If you use different units, these two things will be different. So you need to make sure that your calculator is in the right mode. But if we plug all this in, we then get 1/2 times 1 times 1, so we don't really need to worry about that, times sine of 2 pi over 3. And this, my calculator gives √3 over 4. So this gives us the area of the triangle. We times this by 3 because this area is going to be equal to this area, so this gives you the area of the whole triangle. So the area of the equilateral triangle is equal to 3 times the square root over 4, square root of 3 over 4. The area of the circle, full circle, so the circle area is just pi r squared. So our radius is 1, so it's just going to be pi. And so finally, the area of the shaded region, if we look at this nicely, the area of the shaded region is just the area of the circle, subtract the area of this triangle in the middle, so this sort of like weird circular region. The area is going to be the whole area, pi r squared, subtract our area of the triangle, which is the 3 times the square root of 3 divided by 4, and that's our answer. This is units squared. So have we got any questions? I realise that I'm now 10 minutes over time. Okay, well the very last bit is the unit circle. So what have we done so far? We've looked at the trigonometric functions for right triangles. This allows us to find any length or angle, assuming that we have 3 pieces of information. We've generalized this to any arbitrary triangle using the cosine rule and the sine rule. There are a few ambiguous cases, but we know what those are now. We applied some trigonometry, our idea of triangles, to some geometry problems, namely finding areas of circles and sectors and segments and triangles. And so we're going to finish this talk today by describing the unit circle. And what this kind of does is the trig functions are defined for angles of a triangle, but the angles of a triangle have to be positive, and they have to be, they all have to sum to less than 180. So really, truthfully, angles of a triangle can only be between 0 and 180. So our trig functions, as they are now, are only defined between 0 and 180 degrees, or 0 and pi radians. So we're going to use a trick to generalize our trig functions. We're going to extend it to greater angles. So here I've looked at specifically the triangle in this first quadrant. So it's between 0 and pi over 2 radians, so a right angle. And let's just describe any point on the circumference of the circle using some coordinates x, y. Well, we can describe this triangle, and it turns out that the width we can describe using cosine of the angle, right? Just the adjacent, which is x, divided by the hypotenuse, which is 1. And similarly, the height we can describe using the sine function. So it turns out that these trig functions describe points on the circle. That given any angle, we can then describe that point on the circle using these trig functions. Now, we only know what these trig functions really do when the triangle is in this first sector. But let's kind of swap things around. Let's define the trig functions based on what we expect these coordinates to be, because it matches with what we have for our trig functions for triangles. So we'll use this first thing. We'll calculate one. So we'll calculate this one here. And so we have kind of our unit circle. What is this? Well, this is a little bit less than 2 pi. In fact, if you add pi on 3 plus 5 pi on 3, that looks like an S. This equals a full rotation. So you're almost thinking about, we've gone backwards, if you will. Pi on 3. So what's the sine? What is the height? Right? Because if you think about it, cosine of the angle and sine of the angle are our coordinates because we can use the right triangle. But here now we're plugging in something out of the range of our triangle arguments. But we've generalized it because this is what the height is. The height should be sine of the angle. Well, you can kind of use symmetry to find that height here. We can compare it to the first quadrant again. And so this is simply going to be sine of pi over 3. So what's sine of pi over 3? Oops. Sine of pi over 3. So this is going to be equal to the square root of 3 over 2. So if we draw our circle again, just to make it a bit more clear. So we have our small little angle here. The height is pi over 3. Sorry, is square root of 3 over 2. But we want to find what the sine function is for this whole rotation up to this point. Well, we know that the height here, we don't know what the width is yet, but we know that the height here is going to be negative, right? It's going to be negative pi over 3, because the height here is just the height of this triangle, right? This is going to have a length of 1, because it's a unit circle. The angle is going to be pi over 3, so this length here is going to be square root of 3 over 2. But when we look at the coordinates, this is going to have a negative value. And so that's what this is. This is just going to be negative square root of 3 over 2. And to very quickly do the other problem, to just give you another example, because this can be quite awkward to wrap your head around, we want to find cosine of 100 and 1 radians or times pi. So this means we're wrapping around the circle almost 50 times or so. We'll wrap around 2 pi, another 2 pi, another 2 pi, until we only have 1 pi left, which gives us this point here. So this is going to be cosine of 101 pi, and then the other coordinate is going to be sine of 101 pi. And to find the x-coordinate, well, the x-coordinate should be quite, you can almost see that if we have a unit circle with radius 1, and we want to find this x-coordinate, well, this length's 1. This height's going to be 0, because it's on the x-axis. So this coordinate is simply going to be 1, 0. And then comparing, well, the x-coordinate is going to be cosine of 101 pi, so that's just going to be 1. Oh, no, it's not going to be 1, because this length here is 1, sure, but we're on the opposite side, so this is going to be negative 1. Because again, we're using the unit circle to extend what it is. We know what the length is, but because we're now using these other segments, we're now going in the opposite direction. So I digress. I feel like my explanations are now starting to get somewhat sloppy, but I hope this we can use the unit circle to generalize these trig functions for larger angles, for any angle between negative infinity and infinity. We can also, so now we know that on this unit circle, the sine function represents the height, the cosine function represents the width. And we also, what does the tangent function represent? Well, we can look at the right triangle and notice how, again, tan equals opposite over adjacent. We can divide both the top and bottom by the hypotenuse and not change anything. But then this is equal to the opposite divided by hypotenuse, all divided by the adjacent divided by hypotenuse, which is exactly sine divided by cosine. So our tangent is actually equal to sine divided by cosine. This is true for any angle, for the right triangle or the circle. In fact, we define the tangent to be this ratio, so we can now extend the tangent to more angles. And if you recall the slope function, right, this is going to be the slope of the line, which is the change in height divided by the change in width. Well, the change in height is going to be sine of theta subtract 0, and the change in width is going to be cosine of theta subtract 0. So the slope of this line, the slope of the radial line, is tangent. So cosine is the x width, sine is the y width, and the tangent is the slope. And now we're on the final bit. You can see where we are now. The final part is recall the inverse trig function. So we have maybe tan equals theta is opposite over adjacent. But the inverse tangent of opposite over adjacent is our angle. But so here, in each case, the angle is equal to the inverse trig function. But what's interesting here is if we have a unit circle of radius 1, this is what we've been using, the unit circle of radius 1, well, the angle is equal to the arc length, right? Because the arc length is just the angle in radians times the radius. So the arc length in radians is equal to the angle. So in this case, because the inverse trig functions are equal to the angle, and the angle is equal to the arc length, the inverse trig functions give you the arc length of the unit circle when you measure in radians. And there's actually new notation which often you'll see. Instead of using sine with this script of -1, you'll actually see the inverse sine function written as arc sine. And arc is because the inverse function gives you the arc length. So I've rushed through this last bit. I think everything else was somewhat clear. I think more examples would be better for the unit circle, but we've run out of time. But if I go to here again, When we get to graphs, I will do a brief summary of the unit circle. I just wanted to finish off by generalizing the trig functions for any angles between negative infinity and infinity, not just interior angles of a triangle. So the unit circle is quite a nice way to do that. And that ends the geometry section of these lectures. So I apologize for going over time. Before I stop the recording, are there any questions? Cool. Okay, well, I'll end that here. Thank you for listening. Next week, I will try and go over some graphs and identities. Again, these aren't a replacement for going through lectures and doing examples. Please, please, please do examples if you're learning trig. I feel like these sections would be a tad more complicated, so I might assume more, but if there's any questions, I might see someone typing. Cool. Okay, well, thank you for listening.